Hello everyone, my name is Viraj and today we'll be having post-contest discussion for Leetcode Weekly Contest 424 by TLE Eliminators. So I hope the contest today was fun for you. Let us start. I'll be moving on to the problems. So we have four problems here. Let's begin with problem 1. Make array elements equal to 0. Alright, so you are given an integer array nums and you can start by selecting a starting position current such that nums of current is equal to 0 and you choose a movement of direction for either of left or right. Now, when you do that, you repeat the following process. If current is out of the range, that is 0 to n minus 1, that's the index range that's given, you end that process. Else, if you think that nums of current is 0, then you move in the direction by incrementing current if you are moving right, or if you are moving left, you decrement current. Else, if nums of current is greater than 0, you will decrement nums of current by 1 and you will reverse your direction. That is, left will become right, right will become left, vice versa. And then you take a step in that new direction. So a selection of the initial position current and movement direction is considered valid if every element in nums becomes 0 by the end of the process. Return the number of possible valid selections. Alright, so let us try to generalize this problem and understand what are they saying. So they are telling you very simple stuff. What are they saying is you have an array of n size. I'll call this array A. And this array might have the elements 0 also. So I'll take the first example 1 0 2 0 0 2 0 3. So this is 1 0 2 0 3. Now they are saying that some initial position has to be chosen by you. So I'll call that position current, and some direction has to be chosen by you. It might be left or right, like these are the only two options. So there is some choosing of current index that you start off from has to be done by you, and some direction that has to be done by you initially. And then when you choose these two things, you have to simulate a process. So first of all, for choosing these two things, on direction, there is no boundation. You can either choose left or right in the initial phase, but current has to be started off with an index that is 0. So I can either pick up the index, like if this is 0, 1, 2, 2, then this is 3 and this is 4. If I have a 0 based indexing, I can either pick up the index, you can say index 1 in the start, or I can pick up the index 3 in the start. That's the only case. So let's try to simulate this. What are they saying? Let's say I pick up the index 3 and I pick up a direction left. Then what do I start off with? I'll say that since I've picked up the direction left, I will try to move left. So I'll say, okay, starting at this location, let me move left. Now, what are they saying is, you can move left till you think that there is a number that is not positive. So it's written that if num of current is 0, then you will move in that direction simply by incrementing current if you're moving right, and if you're moving left, then you decrement current. So in this case, since I chose my direction to be left, I'll say, okay, 3 became equal to 2, that is I decremented current and I moved to the left position. But as soon as you feel that the number has gone positive, that is nums of current has become positive, you will decrement that number and you will reverse your direction. So I'll say, okay, if now standing at this location, this number is positive, so I'll make this number to go 1 minus, that is 2 minus 1, that is 1. And now I'll again move right. So I have kind of switched my direction, left becomes right. And then same simulation goes on and on. I'll say, okay, let's move on right. Okay, again a positive value, fine. Let's decrement it by 2 and then come back. My direction changes and I become left. And so on, so on, so on. This keeps on happening, keeps on happening, keeps on happening till what is the target? The target is you are able to convert this array A fully to an array that looks like 0, 0, 0, 0, 0. If you are able to do this, then this initial selection of current and direction as a combination or as a pair is called valid. And you have to find the count of all such valid pairs of current. Of current and direction selection. Okay, so this is a very simulative based process. What we can do is we can understand that why won't some other case also work, so that it creates a clear picture, and then we will take one more case to actually make our whole argument. Okay, so I'll take this to a new page. Let's say this array was what we are talking about 1 0 3 0 2. So even in the test case, they have given an explanation that, okay, why would you can select current equals to 3 and then have a left direction that is going to work. So you can follow this whole process that, okay, starting with this 0, I moved left, so went to 2, then it became 1, changed the direction, went to 0, went to 3, then decremented 3, changed direction, came back to 0, went to 1, so on, so on, so on. Everything is happening, and then you can follow this whole simulation to create 0, 0, 0. So it makes sense that this is not working. Sorry, this is actually working with current 3 and direction left. Similarly, current 3 and direction right will also work. That is a similar simulation. Now, if you start with 0, but you initially choose right, you will first go to 3. Then, because it's positive, you will decrement it, come back to left, go one more left, then decrement it, go back to right, decrement it, go back to left, and so on, so on, so on. This keeps on happening, and you actually receive 0, 0, 0, 0. Now, I'll show you a small simulation so as to prove why is the other index not working. Let's say I would have taken something like this, as in current is initially 1, and then you can say that maybe I chose the direction equals to left. Just a simple argument. Then what would have happened is you would have started with 0, you would have gone to this 1, and you would have said, okay, fine, went to left, this is a positive value, make it 0. Great. And now change your direction. So come to right again. Now this is positive, so decrement it again, and this becomes 2. Great. Now change direction. You can say, now I'll have to change direction, so I'll come to left, and then finally I'll move out. So you can say that there was no other stoppage point on the left hand part, and you basically went out of the bounds, right? The bounds were from 0 to n-1, or basically 4, and you crossed 0. You crossed 0 more on the left hand side. So when you took current as 1 and direction as left initially, you found that this is not valid. And since this is not valid, this was not counted as a valid pair of choosing of current and direction. Same thing actually, if you choose with 1 and right, it's not going to work. So main first of all condition is you choose current to be 1, right? Current to be an index where 0 is kept. So this is the main condition. This has to happen. But after that also, it's not necessary that whichever direction you choose, it's all going to work. We need some more smarter observation in this, that actually what's happening, which is making that current index, if possible, to be an answer, right? Over here, we saw that, okay, there were two indexes, 0 and 0. I just could have not blindly chosen any 0 to be my starting index. Only this index worked, but this index did not work. As we saw over here, this example that we started with, the index 1. So what was so special about index 3 is what we have to observe. Or if we take some other cases like this, you have to also observe that, okay, what was not so special about this index or even this index. Hence the answer was 0. So as in no possible indexes were kept as an answer. That means nothing was true. So what's the valid observation? What's actually happening over here for us to simulate? Now again, the whole idea is this size of the lens array is very, very small. It's 100 in order. So basically, if I tell you that you can brood this whole solution out, you can definitely do that, because since the array size is very low, maybe you can just say, okay, fine, I'll just take some index as my starting position, some direction as my starting position, try to simulate this, go left, then go right, then go left, then go right. And I know since it's only 100 in size, I will not encounter a lot of headache in the simulation part. So I know my solution is going to work. But let's say this n would have been even larger, or as in the nums.length would have been even larger, then it would have been a problem. We need to come up, or we need to generally discuss the best possible solution so that it's applicable on even higher cases. And that is what we are going to do right now. Okay, so that is all going to be becoming very easy once we discuss the observation in this problem and try to visualize this, that actually what's making that index so special if that index is an answer. Okay, let's try to understand this. So you have this array A1, A2, A3, A4, and let's say some numbers, then let's say like A7, A8, A9, A10. Let's say I have a 10 sized array. Now, what am I trying to argue over here is, let's say that because of your initial condition, you pick up some index I over here, for which you felt that, okay, or not I can say current over here, for which you knew that the location, the number at that location current index was actually 0. So you said, okay, maybe for just simplicity purposes, let's say just A4 was that index where the value kept was 0. So this is a good start point. This is something where you have to start off with. But the initial question remains, how do I calculate quickly and smartly whether this A4 index contains that power that if I select this A4 and let's say I'm select some direction, then my answer is going to work. or my simulation is going to work. How do I know that? I know A4 is a starting point, could have been a starting point because it contains the value 0. It's fine, but why does it work, or how could have it worked? Let's try to visualize this part. So let's say from A4 you select any direction. Let's say, just for general purpose, let's say you select left. So you would have gone to left, and when you would have gone to left, you can imagine that there is sort of a wall. Okay, I'll quote this term, wall. You can imagine that any number that falls on the left of A4, any number that falls on the left of A4, if it's positive, is helping you change the direction. Similarly, any number that is kept on the right of A4, is also going to help you change the direction. I'll just remove this. Is also going to help you change the direction. What do I mean by that? Let's say you were at A4. You said, okay, fine, let me move on to left. When you move on to left, any such number which was still positive will make you come back to right. Similarly, if you would have, or if you were traveling in the right direction, any number on the right that was positive will act as a wall and make you come back to left. So try to understand this. You effectively want to make whole of the array as 0. That means, effectively visualize this part, you want that the number of times you encounter the wall in the left, and the number of times you encounter the wall in the right, the absolute difference of both of them should be less than equal to 1. What do I mean by this? As in, simple said, the sum of numbers on the left hand side of A4, that is A1 plus A2 plus A3, and the sum of numbers on the right hand side of A4, that is these numbers so on added up plus till A10, should give you an absolute difference less than equal to 1. Now why is this going to work? Let's try to simulate these cases. Okay, let's just say that the absolute difference turned out to be, like, absolute of that difference turned out to be equal to 0. So I'll take an example, same example. You have 1, 0, 2, 0, 3. Let's say you chose this index. Now, because we simulated the process, we knew that this index is going to work. But understand this, if I observe the sum of elements on the left and sum of elements on the right, what do I find? Sum of elements over here is actually 3. Sum of elements over here is actually 3 also. What is this telling me? Visualize this very cleverly. Can I say that since sum of numbers on the left is 3 and sum of numbers on the right is 3, if I go to left, from left, I will be forced to come to the right again. If I jump to left, I'll be forced to come back to the right again by the wall, basically you can say, effectively 3 times. Yes, that's true. And same thing, if I would have been going in the right, I would be forced to come back to the left effectively 3 times again. So that means I would be able to exhaust all the positive numbers that came on the left and right also, since their absolute difference right now, you can say, is 0. It's equal. So you know that if you choose left or if you choose right, if you choose left or if you choose right, both cases are going to work. As in, choosing this index and choosing left will also work, or choosing this index and choosing right will also work. Because if you choose any initial direction to start off with, you will go to that direction, come back from that direction, then when in the direction which you went to, you will come back again from there, so on. You will kind of play a ping pong tennis sort of a thing, that you will go here, then here, then here, then here, then here, and there, and so on, like this and this. You will just do to and fro, but you will do to and fro the number of times which you felt that was there in the total sum on the left also and the total sum on the right also. Since both of them are equal, you will effectively move to and fro the same number of times, and that will make all the numbers to the left also turn to be 0, and all the numbers to the right also turn to be, all the numbers to be right to also turn to be 0. Okay, this is why I said that the absolute difference should be equal to 0. Now I have said less than equal to 1. That leaves us with one more case. Either it was 0 or I said 1, right? So I'm saying that that index is special or can be worked up with if the difference is less than equal to 1. Then I showed you case number 1, that if the difference is actually 0, then that index with any such direction is a valid pair. So that current index with left also works and that current index with the right also works. Now let's take case number 2. If that absolute difference turned out to be equal to 1. Now, is the argument same? I mean, I'm arguing still that that current index will work, but will any direction work right now? Let's try to visualize this again. Let's say I'll modify the array a bit. It says 1, 0, then this is like 3, 0, 3. Okay. Now you say, okay, this index is something I start off with. Now the sum on the left is actually 4 and the sum on the right is actually 3. To understand this, visualize this part. When you initially started off with any direction of to and fro, because the left and the right contained same sums, that is, the number of times you would have hit the wall on the left were equal to the number of times you would have hit the wall on the right, you were good to go and you said any initial direction was great for me. Either I go left, either I go right. But right now, that's not the case. Why? Let's try to simulate this process. Let's say you choose right. So what will happen is you will go to 3 and like, I'll rub this. So this becomes 1, 0, 3, 0, 2. You'll come back to right. So this is 1, 0, 2, 0, 2. Go back to 2, 1, 0, 2, 0, 1. This is 1, 0, 1, 0, 1. Then this is 1, 0, 1, 0, 0. And then this is 1, 0, 0, 0, 0. And then like initially understand this, you moved right, then you moved left, then you moved right, then you moved left, right, left, right. And then, oh no, you are out of the boundary. Now the argument is, why do you think this did not work? Because you had one extra wall to exhaust or one extra number to exhaust in terms of value on the left hand side, because you knew that the left sum was actually 4 and right sum was actually 3. 4 was greater than 3 by 1. So you can very well see over here that that one extra value on the left hand segment, this is this one actually got left, which means initially if you would have chosen a direction which helps you exhaust this initial value or the final leftover one that could have happened in the initial beginning phase only, then you would be good to go. That is, now if you choose current comma right, this is not working. But if you choose current comma left, this is going to work. Why? Let's try to simulate this again. I'll just rub this out quickly. Okay, let's just see once more. So let's say you started off with going left initially. So you went left. So this becomes 1, 0, 2, 0, 3. Then you came right, 1, 0, 2, 0, 2. Left, 1, 0, 1, 0, 2. Then right, 1, 0, 1, 0, 1. Then left, 1, 0, 0, 0, 1. Then right, 1, 0, 0, 0, 0. Then left, 0, 0, 0, 0, 0. So you basically went then right, then left, right, left, right, left, and then, this is left. And then when you finally came out to left, you just exhausted this one and you said, okay, fine. Now the array has initially all become 0, 0, 0. So I don't worry anymore. So can I say that initially choosing current comma left actually worked? Yes, it did work. And this is the whole argument. If I am getting an absolute difference to be 0, then effectively I have two valid positions. With that current combination with any direction left or right gives the right answer. But if the absolute difference is actually 1, then I can only have one of those particular cases at a valid answer. Now remember, they're not asking to print the indexes and the left and right pair. We just want to count them. So fine, if I find an absolute difference to be 0 and that initial index is also 0, I'll increment my answer by 2 plus 2, and else I'll increment only by answer by 1. Okay, so this is the whole problem. Now this problem might not be very beginner friendly. This is sort of a problem which requires head-on simulation in your head. Of course, the problem having lower constraints, you can always brute force this out. You will find good discussions in the editorial part of the platform, but we wanted to discuss a solution that is going to work relatively faster, because now I have a very good observation, and this observation is all that is telling me if you're able to somehow calculate the left sum and the right sum to a specific index quickly, then you will be good to go. And now we have a very strong weapon on our hand with us, which is going to help us do that. That is called prefix sums. This is a topic that is actually taught in level 2 of TLE. So you might want to check this out. Prefix sums is something that we can use over here to finally get our whole answer. Prefix sums actually is going to help us do something like this. You have an array A1, A2, A3, A4, so on till AN. Then what I can do is I can calculate prefix sum. So this is like A1, this will be A1 plus A2, then this will be A1 plus A2 plus A3. So basically every ith index is going to represent the sum till that index, so on. So once I do that, how am I going to help me calculate the answer? How is this going to help me? Let's say A4 was a valid index. I felt that A4 was something that was right. It could have started with saying that A4 contained the value 0. So I want to check whether the sum A1 plus A2 plus A3 is equal to the sum that is coming after A4. How do I do that? I can simply say, okay, the sum till A3, that would be the prefix value kept at the third index, should be equal to I can mark this with a different pen. You can, if you want to find the segment sum for this portion, that is this right portion, you can say simply, okay, the total sum, that is till an, minus, you can say minus, I'll draw this with red, if I remove the sum till this location, right, this is going to work. Why this location? I can even take till A4, but since the value kept at A4 is 0, so that's not going to relatively change my prefix sum. So even I can take till this part, or I can take till this part also, it's all going to work. So this margin, this whole region, this yellow part of region actually tells me the sum on the right. So I can call this something like a right sum, not a botheration with me. And this becomes my left sum. Now, if they are giving me or the wall sum basically, which we try to imagine in the first picture, if their absolute difference is less than equal to 1, then I know I'm good to go. I can report that I will increase my answer either by 2 or I'll increase my answer by 1. This is the whole situation. Now let's try to simulate this on the case once more. Okay, let's just say you have the initial case, something like this. Let's say I have 1, 0, 2, 0, 3. So the prefix sum will be 1, 1, 3, 3, and then this will be 6. This is the prefix sum, like till in this index, the sum is 1, till this is 1 again, this is 3, and then this is 6. So this is the prefix sum. Now, if I stand at this location, I know that the index is 0, so this is a good starting point. And the sum till this location is actually 3, which is kept at this location, 3. And the sum of the right-hand portion can be calculated by the net sum, that is 6, minus the sum till this location, that is 3, which is 3 again. So you know that the absolute difference between both of them is actually less than equal to 1. Hence, effectively, this is actually equal to 0. So you know answer can be incremented by 2. Had this difference been equal to 1, you would have only incremented the answer by 1. So this is the whole ideology. You can pause the video, first try to visualize this whole simulation case, and then prefix sums is going to help you do that. You should be aware of how prefix sums normally look like and it works. That is going to help you even better. Okay, so this is the whole problem. Let's try to actually move on to the coding part and understand how can we implement this out. So it's going to be very simple, just how we pictured. First of all, I have taken the num size as n. Then I've created a prefix sum vector. I'll call this pre. This is n plus 1 size. N plus 1 size basically means I'm getting indexes till n. So it's going to help me because I'm doing a one-based indexing. Normally prefix sums by standard procedure are calculated in one-based indexing, so that it's better to get the correct answers. So what I'll say is I'll run a loop from 1 to less than equal to n because I know indexes available were till n in the pre array. So pre of I becomes pre of I minus 1 plus nums of I minus 1. Why I minus 1? Because I know I is from starting with 1. So since in the nums array, it's 0 based indexed. So I want indexes to run from 0 to n minus 1. But because the loop is running from 1 to n, so I'll use I minus 1 in nums. Now what happens over here is this basically helps me calculate that till the ith index in a 1 based indexing. I'll mark this over here. Ith index in a 1, you can say in a 1 based indexing, I have found the prefix sums. Okay, this is what I've done over here. Now I have an answer variable. That is actually what I want to return. That would be the number of valids you can call, right? And then I'll run a loop from 1 to less than equal to n. Then I'll say, is that index, that is since I minus 1 is the again index because I want 0 based indexing in the nums array. So if that index is the value 0, only then I want to do something. If it's not 0, then I know that's never a starting position for me. So if it's actually 0, it's a starting position. Then if it's special or not, let's see if it can act as the correct location to start with. Let's see. How do I find that? First of all, I calculate the left sum. That would be pre of I minus 1. So just as we went to the diagram, if you select A4 as the particular or fourth index as the correct part, then till the index 3, you will have the left sum. So I'll say pre of I minus 1 is the left sum. How do I calculate the right sum? Right sum can be till total of till the nth index, that is pre of n minus pre of I minus 1 is the right sum. So you can imagine this total blue section minus this red section. That is what we are getting over here as right sum. Now, is the absolute difference calculated with me? Yes, this is absolute of left sum minus right sum. Is it 0? If it's 0, increment by 2. Else if, is it 1? Is it equal to 1? Fine. Plus plus again, and this gives you an increment by 1, because in this case I know I'm only going to take one direction. I cannot take two directions, but over here I can take both directions. So this finally gives you the whole problem solution. And besides this, never is a case that it's an answer. You can never term that as an answer. So that's all right. And when we come out of the for loop, I know answer variable is going to give me the correct part. So I'll just run this out on the sample cases. You can see that it's giving me the right output, and it's going to work on the main casing also. All right, so now what is the time and space for this? It's very, very optimized, definitely, because even if n was larger, this would have worked. This is running in n order because you're calculating the prefix sum over here. And then this is also running in n order, right? Inside this, everything is pretty much constant. This is a constant calculation. This is also constant calculation. So effectively, you are getting a very good solution. If I write the time and space over here, this is going to be O of n. Now in this case, since n was given in 100 order, so you can say this is O of 100. But even if this would have gone larger in terms of n, this would have worked. And what about the space? Now I am counting some space for the array input. That would be nums, along with same array is the size I'm taking for the pre. So I can say that space is pretty much dependent on O of n only, which is O of 100 in this case. Both these time and space are well within my boundaries. So this is definitely going to work, and my logic is also right. Okay, so this is the first problem. It is a bit lengthier than how standard first problems are, just because of the fact that first of all, we tried to understand the whole concept with prefix sums. You could have much similar to the problem, and that would have been easier. But then again, we want the best solution possible, assuming that n would have gone larger. Those basic brute simulations are available in the editorial. You can definitely check them out to understand how you would have attempted this problem in a very simple and a brute manner. Okay, so this is definitely an optimized version of that. Great, so let us move on to our second problem. Okay, so zero array transformation 1. So basically the second and third problem are almost the same. It's just that it's the second part of this. So assumably it should make sense that if we create some solution for zero array transformation 1, similar or same solution would actually work for zero array transformation 2. So let's try to understand this problem first and see what are they asking us. They are saying you are given an integer array nums of length n and a 2D array queries where queries of I is equal to li comma ri. Okay, great. Now for each queries I, you can select a subset of indices within that range li to ri in nums. You decrement the values at that selected index by 1. And then we are saying our zero array is an array where all the elements are 0. So return true if you think it's possible to transform nums into zero array by processing all the queries sequentially. Otherwise return false. So a subset of an array is a selection of elements, possibly none of the array. And this is what is given in the problem. Let's try to generalize this quickly and see what are they asking over here. So they are saying that I have been given an array. Of course, this is of n size, right? This is the array A. You can call the numbers A1. This is like A2, A3, so on till an. Now you have given some queries. You have been given some queries. This is like queries variable, and these queries are of the type where they are giving you a pair li comma ri. So this li comma ri basically represents the range, right? It's basically saying that okay, if li was let's say 0, and then this was let's say 3, so you're basically talking about indexes from 0 to 3. So I can actually change this array a little bit. So I can name this as you can say 0 based index. So this is like A0, A1, A2, A3, so on till this is A of n minus 1. Now this should work. Let's say I'm talking about 0 to 3. That is this segment, 0 to 3. This is the whole range. Now, once you actually process a range, so it's basically like you can say this is one of the range that's given, so on, there are more queries given to you. So you're trying to process these queries, right, one by one and so. And how do you process these queries? What's the effective meaning of saying when I process these queries? We'll say that if we are currently at a query, we can choose some subset of indexes from this query. So if let's say the range is 0 to 3, maybe I can pick up some indexes of my own choice. That is subset. Subset is a selection of elements of the array. It's not basically
sub array or something, like we don't want them to be continuous. It can be continuous, it might be non-continuous, it can be discontinuous. We can take any some indexes from this range. All that is there to ask is it should be within 0 to 3 if you're talking about this example based query. So we'll say, okay, from 0 to 3, maybe I'll pick up the index 1, maybe I'll pick up the index 3, all up to me. This is sort of a subset. Now I'll say, okay, in decrement the selected indexes you choose by 1. So this number turns to a1 minus 1 and this number turns to a3 minus 1. And then you can say that I have well processed this query. Now I'll move on to some other query. That's the next one, process it, next query, process it, next query, process it, and so on, till I'm able to fully process all the queries sequentially, that is one after the other. And once I have done that, I want to ask whether it's possible that this whole array would have gone to all zeros or not. If I think that yes, by some or the other method of processing the query sequentially by choosing some selected indexes for each query and so on, so on, so on, I think that the answer is yes. I think that the answer can be converted, the array can be converted to a full zero based array, zero numbered array, you can say. Then I'll report a true to my situation, right? I'll report a true, else I report a false. Okay, so let us try to see some case and understand that what are we trying to do. Let's just say that I have taken this basic case over here, or I think this is too basic. Let's create some case of our own. Let's say something like 1, 0, 2, 0, 1. And then the range are 0 to, let's say 0 to 3, that is query number 1. And then the next query is actually 1 to, maybe let's say 4. Okay, this is the next query. So this is the array. This is the array A, you can say array. And you want to process these Q queries. So answer to this is turning out to be true. Why? Simulate this. You will say, okay, went to the first query 0 to 3. So basically I know this range is something, I have the power in this range to decrement any index by 1. So I'll say, okay, fine. Let me choose these two indexes, that is this index and this index. Since they are positive numbers, I definitely want them to go to 0. It's effectively greedily helping me. So I'll make this go down by 1. This becomes 0. And then again, I'll go this by 1. So this becomes to 1. 2 minus 1, this is 1. Process the first query. Great. Fine. Next query is from the range 1 to 4. So this is 1 to 4. Went to this again. Now I can choose these two indexes. This is one index and this is the other index. It's coming in the range definitely. So this becomes 0. And this also goes out to be 0. And now after processing these two queries, I have effectively changed my array to look like 5 zeros. So I know that the answer is true. Okay. Now counteracted to this case, maybe I had something like this 0, 0, like initially I had something like 1, 0, 2, 0, 3, and the cases were 0, 3, and then you had something like maybe I'll call this 3, 4. Now if you process this query, your array would have looked something like this is 0 and then 1, 0, this is not 3, let's start off with this 1. So initially you had 1, I took the same case actually, 1, 0, 2, 0, 1. Now, if you process this query, that is 3, 4, the 3, 4 range is only this much. Now, in this much range, if you process this one number, that is at the fourth index, this definitely turns out to be 0. But can you see that, oh no, this index over here, that is the second index, is actually left with you, and it's a problem. This is index, this value did not change to 1. So this is sort of a leftover index, leftover value, which effectively means that you were not able to convert your array to full zeros. Hence, the answer turned out to be false. And this is like a pretty much good simulation of how the simulation is, how the whole question is looking like. You can actually understand this now with your own examples. You can understand this example 1 and 2 on your own. So you will get this whole idea that what are we trying to do. It's a very simple problem to imagine, not a very harsh problem when it comes to the whole visualization part. Okay, great. Now let us try to understand how do we finally solve this problem. What's the argument? What's our visualization? Okay. One important thing to observe over here is, what are we doing? Like, we are having the power to make some segment or any index in that segment go to that value minus 1. So I'll take this. Let's say you have this array A0, A1, A2, A3, A4, A5, A6, so on. Let's say I have these many numbers. I have 7 numbers basically. Now I'll mark this with blue. Let's just say that I'm marking segments. Okay, so I'll say that maybe after the first query was processed, you said that you had the power to decrement the numbers from A0 to A3 by 1. Let's say after that, you had the power to decrement this range by 1. Let's say you had the power to decrement in the next query this range. Then maybe let's say this range. Then maybe let's say this range. Okay. Let's say this is what you had. Now, I'm not right now exactly processing the queries. I've just marked the segments that I said, okay, for example purpose, let's just say that you had been given 5 segments. I drew them with blue, and the segments marked on the array finally told you that, okay, after processing this query or this query and this query so, you had the power to decrement that number to like that number -1 in this range, and this range, and so on. Effectively, if I ask you, how many number of times do you think A0 can be decremented? Like you have 5 queries, you process these 5 queries, you process this, you process all the queries, and then you asked, okay, fine, I did process them. How many times I could have decremented A0? Now A0 is only coming in this segment. Can you see from A0 to A3, this segment that is coming A0 to A3, it's coming only one time. So effectively, A0 has the power to decrement itself by 1 only. This is a very important factor. Listen to this again. A0 being part of only one segment over here has the power to decrement itself to A0 from A0 to a new number by 1 time only. A0 can become A0 -1. That's all, because no other segment is giving A0 the power to decrement itself. If I talk about A1, things kind of change. A1 is coming in the segment from this also, and it's also coming in this segment also. So basically, if I call for A1, same argument, A1 actually has the power to decrement itself by 2. You can say this is like -1 and this is like -2. Similarly, if I talk about A2, argument changes. It is part of 3 segments now, this, and this. So A2 even has larger power. It can decrement itself by a total of 3 times. A3 is actually part of 4 segments, this, and this. So it can actually decrement itself, you can say 4 times. Same thing, A4 can decrement itself. So this is 1, 2, 3. So this is 3 times. A5 can decrement itself actually 4 times, 1, 2, 3, 4. So this is -4. And A6 can decrement itself 3 times, 1, 2, 3. So this is -3. Now, I'm not saying that I would actually decrement them by this value. I'm not saying that, okay, if A6 had the power to decrement by 3, then I'll decrement A6 to A6 -3. That's not the case. Since, remember, I have the chosen option, right? If I select some query, in that query, if I select some range, if A6 is coming, maybe I choose to decrement it, maybe I choose to not decrement it. It's totally up to me. But I have jotted down that if I have always decremented it, what is the maximum value it could have been decremented by? Now, this is going to give me a very important argument. Initially, you know that A0, A1, A2, so on till A6 are some values. They are some positive values. They could have been some positive values. You are trying to make every value to 0. You're trying to make this 0, 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 so on. Now, assuming that you have calculated these values, that is how much maximum could have a value gone to its current value minus what. Now tell me, if I tell you that, okay, let's say A0 was initially a value 4. You wanted 4 to go to 0, but you said, oh no, 4 was to go make 4 go to 0. I know that 4 should have the maximum capacity to decrement itself by a 4 value. But the maximum capacity of A0 to decrement itself is only 1. So can I say that A0 will ever go to 0? No, A0 number will never make it to 0. But let's say A0 was initially 1. Then can I say A0 can go to 0? Yes, it can. Similar argument, I couldn't talk same thing about A1. Maybe A1 was, let's say 3. If it was 3, to make it go to 0, it would have been a lot of struggle for me, because A1 can never go from 3 to 0 because A1 had the maximum capacity only of 2 times, that is -2. That means A1 right now is not possible, but if let's say it could have been a value of maybe less than 2, maybe it was 1. Then I know from 1 I can convert it to 0, because the maximum capacity of A1 to go or decrement itself was 2 times. Maybe I want over here a decrement of only 1 time, so that's fine. Maybe I only choose it to decrement it once. Remember, it's the maximum capacity. I don't always choose it to do. I can sometimes drop it to do. So maybe I'll say, okay, in one process of one query, I'll not make A1 go by any value, but in some other query, I'll actually make it go by one value. So it will become from 1 to 0, since maximum capacity was 2. So this is the whole argument. You will do the same thing for A2, A3, A4, A5, A6. That effectively makes your whole visualization as that if this maximum capacity, or you can call this as like, maybe I'll call this maximum capacity only. You can say that if this max, you can say capacity, is actually greater than equal to that number, that is AI, or you can say maximum capacity of that ith index only is actually greater than equal to that number AI, then you are good to go. You can say good to go. You will keep on moving and so on. And if you're able to reach at the very end of the array, then fine, great. You know that the answer is true because every index had a maximum capacity greater than equal to its number, its current value. And since it was greater than equal to that current value, I had the option to decrement it to 0. But anywhere if this logic breaks, anywhere if the max capacity turns out to be less than AI, then for that particular ith index, I know I don't even have that much amount of decrements available with me. So how can I make that number go to 0? Not possible. Hence, I will break and I'll say anywhere this condition broke, answer is false. Okay, so this is the whole simulation. You can pause the video and try to understand what I'm trying to argue over here. It's very, very easy to visualize once you get this whole segment logic. The tough part would be how do we implement it out, right? We just assume that this is something you can calculate very well. And after, of course, assuming that this part is calculated, you can get the answer by simply doing these two checks, if and else checks. But the whole argument is how do I actually get these values, right? So actually getting these values, this is again an important concept called difference arrays, or it's basically a sweep line algorithm. Okay, sweep line algorithm, or basically call this difference arrays. This is again a concept that is taught in TLE2. So this is something you might want to check out. All right. So this whole concept is going to help me actually get the whole values, effective values for individually every ith index, telling me the maximum capacity of how much I could have decremented it. Okay. How do I get this? Let's see over here. I'll try to take the same example. Let's just say that you had this segment. So how does sweep line algorithm or difference arrays works is you have an algorithm which says that I have effectively like an array initially. That is the max capacities. This will be again of that much size only. So I have taken a 7 size. So okay, this is 0, 0, 0, 0, 0, 0, 0, 0. Okay, one zero left. So I have 7 zeros. Now what was the segment? Initial, like I'll sequentially write down the segments. This is 0 to 3. Then you had 1 to 5. You can call this as 1 to 5. So this is 1 to 5. Then basically you had the next segment as like 1 to 6, 3 to 6, and 5 to 6. So you can say like 1 to 6, 3 to 6, and then 5 to 6. Now what does sweep algorithm says? It will do something like this. It will say, okay, do like if I call this array as like this is actually called like sweep line. So if I call this array as sweep, so I'll do sweep of L of I plus plus, and then I'll do a sweep of like I'll call this R of I plus 1 minus minus. This is what it says. So these are like the two statements I execute for every you can say query. So I'll go to this 0 to 3, I'll process 1 to 5, process so. So if I go to 0 to 3, what will happen is if this is the index 0, 1, 2, 3, 4, 5, 6. So what I'll say, okay, increment this index by 1 and decrement the next index of 3, that is 3 plus 1, 4 by minus 1. So this is, decrement it by minus 1. So you will have this as 0 minus 1, this is negative 1. Now what has this done? Try to visualize this over here. You wanted to mark off this segment, okay? You wanted to mark this segment from 0 to 3, and marking this segment would have actually told you an information that, okay, any such index in this segment right now can be chosen and can be operated upon. So how do I mark this? I have said, okay, to create that boundary, I have effectively marked the location like this, that I have incremented this position by 1, and then borderline next position to that last position by minus 1. So it has kind of created a boundary. From here to here, I have created a boundary. How is that going to come into more visualization? Just be patient and I'll explain why. Let's just process the next queries first quickly. 1 to 5, so this turns this value to be 1, and 5 plus 1, so this turns out to be negative 1. Okay, this becomes negative 1. Process this query, next query, 1 to 6, so this becomes actually 2. And 6 plus 1, so I know 7th index is not there. So I know I can just ignore this part for now because I know 7th index is not available to me. So again, process this query. Again, Ri plus 1 should be available to me. If it's not available to me, I don't need to process that. Now 3 to 6, okay, so this is plus 1. And then 6 plus 1 is not there, so effectively, don't worry, not processing that. 5 to 6, okay, this becomes plus 1. And 6 plus 1, 7 is not there, no problem. I think I processed one of the segments wrongly. We had the segment from 2 to 5, right? And then you had 3 to 6, and then you had 5 to 6. Okay, so this segment was actually 2 to 5. Where is the segment? Yeah, this is actually 2 to 5. So we can say that basically I incremented 1 to 5. So we don't need to do that. This can be the value as 1, and this can be as the value 1. Okay, much better. So now we have processed the last query also. Now, let's come to the main logic. You can see that I have created some array that looks like 1, 1, 1, 1, negative 1, 1, negative 1. It's not still looking like this array. 1, negative 1, sorry, it's not negative 1. This is this negative symbol I drew just to show that this was the maximum capacity, how much we could have decremented. It's basically 1, 2, 3, 4, 3, 4, 3. It doesn't look like this now, but it will actually start looking like this because what does the sweep algorithm now says? We want to run a prefix sum algorithm on the sweep array. So I'll say, okay, calculate prefix sums. This is 1. Till this index, the prefix sum is 1. Then till this index, it's 2. Till this index, it's 3. Till this index, it's 4. Then till this index, it would be 4 minus 1, this 3 again. Then again plus 1, 4. And then again minus 1, this is 3. Now actually look at this array 1, 2, 3, 4, 3, 4, 3. And come back 1, 2, 3, 4, 3, 4, 3. This is voila, what we wanted to do. We have processed the queries and we have actually gotten by our sweep line algorithm the effective maximum capacities that were available for me for every, you can say, overall, every particular index I. Now, I just want to check for that index I, is that maximum capacity greater than equal to AI or not? If it is, great, good to go. Get me going, reach the end. But if anywhere you can break, anywhere you think it's not true, return a false directly. Okay, so this is a problem. This is the main problem finally. It's typically a very theory-based and concept-based problem. All right, so if we'll actually run this on our initial example only, so I took something like 1, 0, 2, 0, 1, and the queries that I processed was 0 to 3, and then the other query I processed was 1 to 4. Okay, so I'll do this only 0, 0, 0, 0, 0, then 0 to 3 process, that is, this becomes, so first of all sweeping, so this is 1, and this is the third index, so this remains as it is, but 3 plus 1, this becomes negative 1, then 1 to 4, so this becomes 1, but 4 plus 1 is 5, 5 is not there, so no problem. Process these two queries, sweep line is done. Now run a prefix on this, 1, 2, 2, 2, 1. Prefix is also done. Now forget about this array, this is not of botheration to me anymore. From this array, check every number. So comparing this number and this number. I know that this is the max capacity for this number. 1 is of course greater than equal to 1, great, good to go. 2 is greater than equal to 0, good to go. 2 is greater than equal to 2, good to go. 2 is greater than equal to 0, good to go. 1 is greater than equal to 1, good to go. So at all locations, I was good to go. That means at the very end, I would have returned a true. But if this argument, this sweep from the sweep line, if this initial queries would have changed a bit, how we processed our one of the other cases that I showed you, that is 0 to 3 and 3 to 4, just a sample case I took on my own, you would have actually observed that we gain a false answer. Okay, now you can pause the video, visualize this first. This is very important algorithm. It's visible many number of times when we talk about array-based questions, right? That's the sweep line or a difference array calculation. It's present in TLE level 2, so definitely check this out. And this algorithm is one which helps us visualize the segments. And after that segment visualization is done, you can pause the video, and if you drew some test cases on your own, you will understand that, okay, working with the sweep line on those sample cases you take on your own is actually giving you the right answer. Let's actually discuss the code part now to understand how do we implement this out. Okay, so just how we imagined, it's going to be very, very simple. We'll say that, okay, I took the size n, that is nums.size. Then I have the sweep line array with me, that is of n plus 1 size. Now I want to process all the queries, so I'll go to every query. And then IT of 0 is going to be the left, or Li. So basically I increment sweep line of L by 1. And if ri plus 1 is actually less than n, that is in the range, that is what we discussed, I want to decrement that particular index in sweep line by -1. So it starts with 0, all zeros, and then this is how I do it. Then what do I say? I'll say, okay, now I want to run a prefix sum calculation on this. So I'll again go to the indexes from 1 less than equal to n and run this sweep line algorithm, that is sweep line of I plus equal to sweep line of I minus 1. Great. Now I have a flag variable. I'll say, okay, go back to the indexes 0 to n. If you feel that sweep line of I anywhere is less than nums of I, then make your flag to be 0, because then you know that, okay, yes, I know that for sure over here my max capacity was not fulfilling, or that value sweep line of I was not fulfilling. So I don't have the available decrements with me, so nums of I will never change to 0 and flag will become 0. And now if I come out of this loop, if flag still remains 1, answer is true, else the answer is false. Okay, now what is the time complexity? You are running basically the queries over here. So queries I think were given in 10 power 5 order. So I'll call this like O of Q only. And then inside this is pretty much constant. Then this is running in n order. So I'll call this as n order. And then this is also in n order. So effectively you are running a solution that looks something like TC of O, like this is O of Q plus n plus n. This is basically like Q plus n only. So whichever is the bigger term, maybe n is bigger or Q is bigger, that is going to be your answer. Now, because n and q both are in 10 power 5 order only, so maximum of that can be taken effectively only in 10 power 5 order is what the problem will go, which is fine. Now, what about the space? Space would be like dependent on the queries also. You can say like some whatever is the size of queries that's given to us, that is this vector of vector, or the nums array, which is effectively in 10 power 5 order only. So somewhat like you can say like q into 2, because for every query there are 2 positions I'm storing in the vector, or you can call this as the nums array, that is plus n. So it's like somewhat a approximation of looking like this. This can be called as q plus n only. Okay, so this is the space. So effectively the time and space are pretty much great for us. They are definitely going to work, help us achieve the right answer, and this is where we can end our second problem. I hope this was understandable. Okay, so problem 3, zero array transformation 2. Now this problem is somewhat the same as the zero array transformation 1 problem only. All that they are saying is, now you have this range Li to Ri, but rather than saying I can decrement the number in that range by 1, I can decrement it by at most val I. At most val I means that I can decrement it up to val I. I cannot decrement it greater than val I. So if let's say val I is 5, just assumption, then I can decrement it either 1, 2, 3, 4, 5, but I can not decrement it by greater than 5, that is 6, 7 or so on. Okay, very, very simple thing. This is change number 1, and change number 2 is actually, now you cannot process all the queries. Initially we had said in this problem that we want to process all the queries and then I want to see whether I got zero error or not. But now the problem is not asking a true or false for that case. It's saying that you have to tell me a minimum possible non-negative value k, such that after you process the first k queries in the sequence, you make the array become a zero array. If you think such a k exists, you will say, okay, great, else you will return a -1. This is actually what is given to us. So now I cannot process all the queries. I want to process only the first k queries, and on that k value is something I want to find how much minimum queries I want to process, in which I will create a zero array, or I will have the possibility to create a zero array. Else I'll try to figure out that, okay, no, this k is not possible, or no such k is possible, so I'll say -1. Okay, now great. First let us try to see these changes and say that, okay, if I understood the problem 1, then maybe I want some sort of a same solution in problem 2 also. And now that I have understood that there are 2 changes in this, let's try to tackle all the changes one by one. So let's just forget this change for first, that is this atmos val part. That is effectively the processing of queries thing. Let's first see this k value. Okay, how do I get this k, or what is this, like what sort of a nature does this k value contain? Okay, so let's go back. Let's try to understand something very, very important. Let's just say that for assumption, you had the possible, like, because k is some number that is in this range of 0 to, either you process 0 queries or you process all the n queries. So I know that I am talking about processing 0 queries, or I process all the queries. And since this is the range in which k can belong, let's try to understand one thing, that if you select some value in the 0 to n, let's call this value as x. let's just say that for some time being, I process the first X queries. Then the argument is, if somehow you received the answer true, if I told you that processing first K queries will actually make the array as 0 array, then if you processed queries X plus 1, queries X plus 2, queries X plus 3, so on till queries N, the argument is, it's very simple to visualize, the argument is you will still find your answer as true. Why is that? It's very simple. If you have processed the first X queries and you were able to get a 0 array, that means this extra X plus 1 query is sort of futile to you, right? Even if you process that, it's not a worry because in X queries only you were able to turn array into a 0 array. So if you process this X plus 1th query, X plus 2th query and so on, even more queries after X queries, it's not helping anyone, right? It's not helping you to say that the answer turned now false. You still know that the answer will remain true. You will still be able to convert the 0 array to a main array to a 0 array, which means that the nature of the answer is true after a limit. So if I call this let's say if actually this answer X was equal to this K, that was the minimum value, then over here the answer is true, and after that all the values will contain the true answer. But before this the answer is actually false, which means, can I observe that there is a monotonic predicate state to K, predicate state to K? Yes, there is, and this is hinting me to binary search on K. I can run a binary search on 0 to n as low and high boundary, and I can say, okay, let's find a mid. For this mid, that is for up to this mid, sorry, not up to, for this number of mid queries from the start, if I process these queries sequentially, what's the answer? Do you get a true? Do you get a false? Let's say you get a true. That would mean that any answer after that is also true. So you will bring your high to true mid minus 1 and you will note this mid as an answer because you know this is a potential answer. I want to minimize my answer. So maybe you land up somewhere like over here. So you want even to go much on the lefter part. So you will make your high to mid minus 1, but you will note down this answer. Else, if this for mid query part, you get the answer to be false, you never note this answer, but you bring your low to be mid plus 1 because you know if this is false, everything to the left of this is false. So I no need to search in that and I can halve my search space. This is the whole idea. Okay, so this is how we have tackled problem 1 in our code, that what was this whole processing first K queries part about, right? I can now find this answer K by binary searching on this answer. By proof I've shown you it's a monotonic predicate state on that K value. Now let's tackle the second problem. Second problem or second change in this problem as compared to the problem number 1 or problem 2 to be specific was that you had at most val as a particular value you could have decremented. Now the question is, it's not very tough to imagine that it's not harming us anyways, right? Our initial code that we wrote was talking only about when I increment or had the power to decrement by one value. So we said, okay, run a sweep line algorithm, but only use 1 as your parameter because that is the maximum change you can bring into your answer. Right now, the only change that is happening is you cannot bring a change of 1, but you can actually bring a change of val I or up to val I. Now, greedily, I can say, okay, let's always make changes of val I and then find out what's the highest change or max capacity, that was this variable you were talking about. Max variable capacity you can actually make still. Same logic, can I not say that, okay, in this piece of problem also, I'll just use this same code, but rather than using this value 1 as constant, now I have been given one extra value, that is that val of I. So now I will run this sweep algorithm on that particular for that particular mid value in binary searching, and I'll get the answer true and false whether that mid value is possible or not. And to get that, I can use just this piece of code. I literally just copy paste this. You will see when I show you the code part. I can just copy paste this same piece of code and I can say that, yeah, just change this one line, that is now you don't have the power of 1, you have the power of val of I. So you can make a sweep line on plus equal to val I when you want li, and for ri plus 1 you want negative val of I. And once you do that, same thing, find the prefix, compare with every maximum capacity. If you feel you're good to go every time, then flag still remains 1, return a true, else you return a false. Okay, so this is the whole argument. This is also going to work on problem 2. So I hope this is understandable. Problem 3, this is going to work on problem 3. Problem 2 I explained very clearly. So if you can pause the video, maybe go back to the problem 2, you will understand what did we discuss when we discussed line sweep. The single change that I'm bringing into picture is now we don't have the power of 1, we have the power of val of I. So if you look into our code now, it's going to be very, very simple to understand. First of all, this min0 array, I'll start with this. I'll say, okay, n is the variable. Low is starting with 0, high is with queries.size. That is basically this n value. Now you know answer is -1 because if answer is not possible, you start with -1. You run a while loop, that is the binary search, classic binary search, low less than equal to high, calculate a mid, then check for is possibility on that. If that's true, you note that as an answer and you make high to be mid -1, else you make low to be mid +1 and you report your answer as the correct value. And how do I check is possible? Can you see that this is the same piece of code only, right? I'm using almost the same piece of code, just that rather than incrementing by 1, I am going to increment by, like I'm only incrementing by queries of I of 2, which is actually that val value. And one more change is I cannot process all these queries now. I want to only process the first k queries. So once I've passed this mid value over here in the is possible function, this becomes my k. So I'll run a loop from 0 to less than k, that is processing the first k queries only. So sweep line of queries of I of 0, queries of I of 0 is li plus equal to val of I, that is queries of I of 2. Queries of I of 1 is ri plus 1 is if it's in the range, then decremented by queries of queries of I of 2, that's val I again. Okay, same line sweep algorithm, then run a prefix sum on that, make a flag variable, compare again, return and true false or accordingly. Okay, so this is the whole idea behind the third problem. Also, now let us discuss the time complexity. Very, very simple. You have n over here. I think it was in 10 power 5 order. So basically, this is a binary search where you have the search space as your time complexity. Since search space is almost 10 power 5 order. So this is like log base 2 of search space. So I can say this is 10 power 5. This is the binary search, and inside this, the is possible function, that is we discussed previously also, is the same logic only. So it's running in basically n complexity to be specific. This is n order, and then this is like k order. So this is like k order over here. This is n order over here for the line sweep only. Okay, maybe I can run the line sweep till k also, not a big problem because I'm only processing the first k queries, but it's fine, not a big deal. And then you have n order over here also. So roughly this is something like O of k plus n. Okay, now if I calculate the final time complexity, it turns out to be something like O of log base 2 of n into k plus n. Whatever is the larger term turns out to be the main answer. Alright, this is the whole problem. This is the whole idea. This k should also not be equal to written like this. Maybe this can also be written as something like n only. Effectively, like the whole solution is coming out to be n log n. To be very generalized way, this is n log n as a problem, and n log n is going to work, of course, because this is within this boundary. It's even if you take queries into process of terms now, right? If the queries loop is something we want to picture, then it's 10 per 5 order maximum over here also, 10 per 5 maximum order over here also. So even if this is n or q terms, this is maximum 10 per 5 order only. So the plugged in values are 10 per 5. We can report this as n log base 2n also, or maybe n if you may make it more acutely, but still it would be in this 10 per 5 into log of 10 per 5 order only, which is going to work. And what about space? Now in space, I'm using this extra sweep line array, of course, that is of the n size, and there will be some size of the nums array, some size of the queries array. So effectively how we discussed previously, the space was q plus n. We can also report this as q plus n only. Okay. So this is the whole idea. This is the whole problem. It's basically an extension of problem 1. So if you have understood the problem 1, this second problem should have been a 5-minute problem for you, because all we wanted was to apply a binary search in this, and just a single line code would have changed of how do we sweep line on this whole array. Okay, great. Now let's come to our fourth problem. This was relatively a harder problem. You are given an array of integers nums. Some values in nums are missing and are denoted by -1. You can choose a pair of positive integers x, y exactly once and replace each missing element with either x or y. You need to minimize the maximum absolute difference between adjacent elements of nums after replacements. Return the minimum possible difference. So let us say that the nums array look like 1, 2, -1, 10 and 8. So this -1 is something that can be replaced. So what are they saying is, you pick up 6, 7, and if you replace this number, let's say with 6, so it's option, you could have replaced with the 7 also, but arguably if you replace this with 6, then you create an array that looks like 1, 2, 6, 10, 8, And then you can find the absolute differences. The absolute differences out of this, the maximum absolute difference is actually 4. Hence the answer is 4. And this is arguably the best we can do. Hence the answer is 4 to this whole problem. Alright, sorry, this sample case. Okay, so let us try to generalize this problem first. What are they saying? It's been said that you have an array A with you of n size. Okay, so n size, array A, some numbers, A0, so on till an. Some numbers are positive, some numbers are negative 1. So the numbers that are negative 1 are replaceable, and you can replace these numbers. Now, when you want to replace these numbers, you want to replace these numbers with some chosen x or y that you have already selected in the start. So you are saying that I had chosen two numbers x and y with me. So x comma y was already chosen with me. And then I said, okay, after choosing this x and y with me, whatever negative 1 occurs in that array, I either make that negative 1 x or I make it y. It's totally up to me. What's the target? The target is after you have filled all the array, as in you have replaced all the negative ones with x or y up to your choice, you have a new array. Of course, it looks like A0, so on till an, but all the numbers are having some value. They're not negative 1 anymore. The negative 1 replacement have been done. After this modification has been done, what do I want to say? I will calculate the absolute value of the adjacent differences. Absolute adjacent differences. Yes, all right. And then you say, I want to minimize the max of this. Okay. So whatever turns out to be this value, whatever turns out to be such values, that is absolute adjacent differences, out of that you want to minimize the max of that value. So you can write this as something like this. You say, okay, A0 minus A1, you calculate this, A1 minus A2, so on. All these will be adjacent differences in this new modified array. Calculate all of them and then minimize the maximum. So that is what is done over here. You can see adjacent differences were calculated. And then I said, whatever is the max in this, choose that. It turned out to be 4. I wanted to minimize this 4 even further. Now I could have not done any better than this. That's why the arguably answer was output as 4. Okay. So this is the whole problem. Now the constraints are very large. It's in 10 power 5 order. All right. And the numbers are also in 10 power 9 order. Now a 10 power 5 order hints me that I'm not looking for a solution that runs in n square or sort of a complexity. Either I run something that looks like n log base 2 of n. All right. Or something like O of n. Or anything even lower than this might work. But something in this order is preferred over here, since n is in this order by experience. Okay. This is point number 1. Point number 2 to be observed over here is you're trying to minimize the maximum. All right. So this whole analogy of minimizing the maximum is somewhat which hints us towards binary search solutions. Now it might be obvious when you look at this problem, how do we implement binary search, or is this a binary search problem? But then it's a good place to start because that is how normally problems come up to be. All right. Even though if this is by experience not known to you, we can actually try to get in our head that what is the argument and why binary search might be a good solution for this. Okay. So now what are we trying to argue over here is, first of all, this difference that we are trying to calculate, this maximum absolute difference that we are trying to calculate is basically a value on which we can binary search. Now, why is that? Like, let's say I am saying that I calculated a minimized absolute difference to be x. That means that I said when I finally placed or replaced the array elements, my new array looked like something like A0 to A of n minus 1. Every number was filled. I knew that every adjacent difference was less than equal to x. So if the absolute differences are less than equal to x, of course they will be less than equal to x plus 1, x plus 2, x plus 3 and so on in a very generalized way. Yes, that's true. That means if I found an answer to be true for this less than equal to x value, I know it would be true for all the above values also. But if I feel that I was not able to even get like all the absolute differences to be less than equal to x, then it's not possible to get them less than equal to x minus 1, less than equal to x minus 2 and so on. So you know that you are kind of getting a monotonic predicate state over here on this absolute difference. You can call this as a max diff variable, and this can be binary searched upon. Okay, this can be binary searched upon. It has a state like false, to true, and you're basically trying to find that first true that would be the least maximum difference possible, and hence this is going to be your answer. Okay, so this is what we are trying to look for. Now, this is not a very beginner friendly concept. Okay, this is part of an advanced concept of how do we realize maximum differences work in binary search. This is actually part of content for TLE level 3, so do check that part out. Alright, once we understand this, okay, max diff is something I can binary search upon, we are understanding that we are trying to create a complex a solution that looks like in n log base 2 n order. Now, in this log base 2 n order has already been covered because I understand this is binary search, so I would be searching on this space, and that would give me a log base 2 of a complexity to actually binary search out. Now, in a binary search, in a simple binary search, when we want to say this is a max difference, we want to now extend this idea and say, okay, fine, you figured out that there was something as a max difference you wanted to binary search on. How do you check this true and false condition, for which you would require a checker function? And the main logic or the main idea of the problem, why the problem actually is hard, lies in this checker function. How do we create a checker function that runs in O of n complexity overall, so that you get a net complexity of n log base 2 n, so that I'm able to run the problem efficiently and I'm able to get the right answer? How do I check whether a selected max difference, whether a max difference that's chosen by me is feasible? Okay, now for this, we would require some strong visualization. So try to follow up with this part. Okay. Now, what I'm arguing over here is, first of all, understand this, that you have this array A in which you have some positive values. Okay, so there is some positive values. So I'll just name those positive. So I'll just leave this as blanks, the positive values, and then you have some -1, positive values, -1, positive values, -1, and so on. This is like a general array I've drawn. I've drawn that blanks are basically the positive values, greater than 0 values actually, and you have the negative ones which you want to replace. Now, try to understand this argument very simply, that let's say I'll talk about this -1. Okay, imagine I have this -1 with me. There is a number A over here, there's a number B over here that is already filled. Okay, for generalized purpose, let's just assume that, okay, so this is array, I'll take this as ARR. Okay, so that I don't use the same variable, this is ARR. Let's just assume right now that A is less than equal to B for general purposes. Now, you obviously want to replace something with respect to this -1, you want some other number to go to this -1. The question that comes over here is, what can be this value? Like, what is the range of this value? What can I make this value to maximum go to? Now, this value, -1, if I talk about, like, if there is a max diff with me, and I'm trying to check for this max diff, then if this -1 becomes A plus max diff, or this value becomes B minus max diff, then can I understand that this is a feasible value? Yes, for this -1, it's a feasible value. So imagine this again, A is less than equal to B. So if you want to make this negative value replace -1 value, replace something, either you can make it A plus max diff. If you make it A plus max diff, you will get a difference of max diff between this A and this new value now, whatever you replace this to be. Exactly, that would be max diff only. Or you can make it in a minimum case. So this is sort of a minimum value that can happen to it, or a maximum value that can happen to is B minus max diff. That was B was greater than A, so B minus. So it's basically saying that somewhere between A to B, I choose a value and I keep it over here. Either that value is A plus max diff or that value is B minus max diff. In both these cases, I will definitely get a max difference possible with either A or B. That's for sure. So let's just say that I keep it A plus max diff. Okay, A plus max diff. So now what's the issue? This becomes A, this becomes A plus max diff, and this becomes B. Now when you calculate the adjacent difference for these two values, that is A plus max diff minus A, you will get max diff. Yes, that's true. But when you calculate the absolute difference between these two adjacent values, that is A plus max diff and B, it's not sure that you receive a value that's actually less than equal to max diff. It's not sure. You will write this value as like absolute of B minus, then this is A plus max diff. So it's not sure that I actually am saying that this is less than equal to max diff. It's not sure, but then there might be a possibility that it is. If it's not, then we know that we want to change our answers. This max diff won't work for me. And same thing can be checked with this part. First time we said, okay, I want to replace this with A plus max diff. Maybe we could have replaced this with B minus max diff. In this case also, I would have wanted to check later on whether this worked out for me or not. And now try to imagine this simple case that what I'm trying to do is, if you have the value as not a -1, you are basically introducing boundaries. Okay, you are saying that, okay, if this a number was there, then for this a number, if it has an adjacent one, so in this case it did have an adjacent one, then a plus max diff, you can say a plus max diff and a minus max diff could have been possible values. Okay, this could have been possible values. This could have been a possible value for the minimum I could have stored, and this could have been the maximum value for maximum I stored. Now, mapping these min and max to x and y. Remember, we are trying to find two values. Either we are trying to find two values, x and y. That is why I'm taking this min and max. What I'm trying to say is, okay, you get a min and you get a max value. You make this min value always as x and you make this min value always as y. So you generalize all over this also, that x is less than equal to y. Now starting over here, we can say that effectively, let's just say that I've taken an array, okay, and like a0, a1, a2, a3, so on till an minus 1. And let's just say I have removed all the numbers which were -1. So there are some gaps that are created. Okay, let's just assume like this, something like this. Let's say this is a0, then there is some gap of -1s, then there is a1, some more gap, then a2, alright, and some gaps and so on, so on, so on. And then you have the last number as, let's say, an minus 1. So we have some gaps in between. Okay, not bother with that part. Those gaps are of -1 gaps. Now imagine that for generalized purpose, I'm saying that this array is increasing. So a0 is less than equal to a1 is less than equal to a2 is less than equal to so on till an minus 1. So I'm saying that this array is increasing. These numbers are falling in an increasing order. What do I want to do? Imagine that you choose an x and y, which is the min and max. So effectively, for every value that is a0, a1, a2, so on till an minus 1, I will calculate a0 plus max diff, a1 plus max diff, a2 plus max diff, and so on, an minus 1 plus max diff. And similarly, I'll calculate a0 minus max diff, so on till an minus 1 minus max diff. Now imagine over here, you have a lot of possibilities for x, you have a lot of possibilities you can choose for y. Which value should you take? Preferably, you should take x as a0 plus max diff, and you should take y as a of n minus max diff. Why is that? Imagine this again. I'll rub this out. Imagine this simple visualization. So I'll draw this with a different pen. So I'll draw a number line, okay, like this. And I'll say, okay, I had this, let's say, number a0. Then this max diff, I want to add this to that. So I'll say, okay, in this case, let's say this is the segment of max diff. This is like plus md. Great, good to go. Then let's say there was something like somewhere like a1 over here, somewhere like a2 over here. So now for this also, the segment of max diff somewhere extends like this. I'm just like drawing rough lines over here of the same length. This is also plus md, okay. So this is like plus md over here. Now, once I say that, okay, I have this every individual numbers plus maximum difference value on this segment, what should I choose as x? X being less than equal to y, what should be x? Of course, x should be this value y, because like x should be chosen as a0 plus md. Why? Because that value will look somewhere like this. This is x, right? This is x. Now imagine if this is x, then you are in the boundary to create a maximum difference with a0. You are efficiently in a boundary to create a maximum difference less than equal to, a difference of less than equul to max difference with a1 also. And definitely you are with a3 also. So you are good to go. If you choose, let's say you could have chosen this value, that is this value as x. Now you did create a MD with a2, but you would have never created less than equal to the maximum difference less than equal to maximum difference with a0. So that means it is preferred that I choose the extreme interval, that is this a01. And if I apply this same logic vice versa, it would make sense that from an minus 1, basically, if I have minus md as a segment, this is like, you can say, I'll draw this below this. This is like a minus md segment. And then you have like, let's say an minus 2. This is again a minus MD segment and so on, I would prefer that I choose this value over here as y, because then this y will create less than equal to maximum difference. Of course, it's creating with an minus 1, it will create with an minus 2, and it would have higher chances to create with an minus 3, an minus 4, and so on, so on. So this is the greedy approach that we are trying to do. This is the greedy approach that we are trying to do, that if I have a lot of available options in this for every number plus max diff and every number minus max diff, in these boundaries, in the segments, I want to stab 2 points greedily, and find x and y, and those x and y should be preferred that it is the lowest number, that is, since a0 is the lowest right now in this whole array, that lowest number plus MD max diff, and y is actually the highest number, that is, you can say an minus 1 minus MD in this range. This would make sure that I have the correct x and y. Now for this x and y, once I have chosen x and y, I want to start replacing the numbers. I've said, okay, x and y came out to be as expected. I approximated that this x and y would work for me, but it's not sure, right? It's not sure. Why? Because we discussed this case that maybe you place this number as x. This was a plus max d, so maybe this was x, you placed it, but it's never sure that this x actually creates a difference of less than equal to max diff with the next number that was occurring positive b. It's not sure. So you will have to cross verify again. That is why, like, I can imagine this once more. Try to imagine this, that in this range over here only, you could have chosen this as x, like somewhere, I'll draw this with a red pen. Somewhere you chose this to be x, it created good differences with every number. Somewhere over here you chose to be y, it created good differences over here. But next case could have been that between this, you still don't have a difference that is max difference. Maybe you create a difference, let's say this difference was d, this difference turned out to be greater than max difference. So that violated your condition again. That's why you need a cross check. Once you place x and y, you need a cross check to do. Now this creates two cases for us. What do we want to place? Either you say that you have, in a generalized way, you have a less than equal to b, that is, you have a pair of segment, a is over here, b is over here, and then you have some distance to fill in this, some negative ones to fill in this. So case 1 can be you only have one negative one to fill. If you have only one negative one to fill, then you can either fill it with min value or you can fill it with max value. That's totally up to you. But second case can be you had, like this was a single negative one, you had a and b, and in this you had more than one negative ones occurring. Maybe you had 3 negative ones occurring, or maybe 4 negative ones occurring. Now what should you do? It's now greedy choice. Why? Over here what we can say is, since we generalized a was less than equal to b and x was less than equal to x was less than equal to y. If I ask you over here, should you place x or y? Y is larger or farther to a. Since over here it's a, y is farther to a than compared to x. So would it make greedy sense that I place y, or will it make more greedy sense that I should place x over here? I should place x over here. Same thing for the next negative one. After I have done that, should I prefer to first check if I can place y, or should I prefer to first check I should place x? Of course, I should first try to place x. Then maybe after a limit, I'm not able to place anything like any x's anymore. So I will try to place y after that. That's not a point. But the argument is, which is that first value you should check, whether you should try to place x over here or whether you should try to place y over here. And of course, you will first try to place x. So the whole problem justifies to, first of all, we understood that we wanted to binary search on this max difference. That was done. Once we understood that we could binary search on this max difference, we wanted a checker function in O of n. To calculate this checker function, we said, okay, first of all, let's understand, for every value that is not -1, we are kind of having boundaries that are created. We are saying that the boundaries are a plus max diff or a minus max diff. This is the boundaries that we're trying to create. Now in these boundaries, we are saying that, okay, once we have these boundaries for all the numbers, of all such numbers, greedily, it would make sense that I take x to be the boundary that is least number a0 plus md. This is x. And the y should be the boundary that was the largest number minus max difference, that is y. Why did I do that? Because this relatively increases my chances to create less than equal to MD differences with all the other numbers chosen. I could have kept the value as x or y. Now, because I had two values to kept, I further bifurcated to these two cases. Either I say between the segment I had only single negatives, or I had more than single negative ones. That means if I have a single negative or I have more than negative ones, now I need to question myself, where do you want to start off with? Do you want to start off with checking as X, or do you want to start off with checking as Y? So we generalized the case. We said, okay, fine. Assuming that A was less than equal to B, then we would have preferred to keep X first, since X is closer to A as compared to B, because X is less than equal to Y. So don't keep Y first. Try to keep X first and then try to keep Y first. Once you do that, once everything is done and dusted, now for cross checking, to tackle this case, maybe it could have happened that even after keeping X and Y's, the difference between X and Y was not less than equal to MD. It actually crossed maximum difference. So for a relatively better check, finally after you've done all the replacements, make a brute check on the main replaced modified array once more with every adjacent differences. Are they within the boundary or not? If they are within the boundary, then you know that this max difference was good to go, because you were able to find some X and Y values which satisfied your condition. And hence, this max difference is good to go. You will bring your high to mid -1 and you can note this as an answer. Else, if you think this max difference is not good to go, you can bring your low to mid +1 and never note this as a potential answer. Find this first valid true, and report that as your answer. Okay, so this is the problem. It's a relatively very tougher problem, I should say. Let's try to actually simulate one of the cases over here to fully understand this problem. We have these cases over here, like this case 1, 2, -1, 10 and 8. So I'll just take this part. Like I have 1, 2, -1, 10 and 8. Okay. Now just to like imagine over here, we knew that 4 was an answer, but then we are saying that it's the minimum maximum absolute difference that we can create. Okay, so now let's say I was binary searching and I was starting with 0 and I had a very large value, maybe like 1E9 or something like that, and I found a mid. Okay, so let's just say I found a mid, or maybe I can dumb this down. Maybe I only have till 10. Okay, so I'll say I calculate a mid. So this is 0 plus 10 by 2, that is 5. So 5 is a mid. This is my max difference right now. Let's just check with this part, equals to max diff. Let's just check. So first I find the lowest value in this, in all the numbers which are positive and have a -1 in their adjacency. So this is a number that has -1 its adjacency. This is a number that has -1 its adjacency. No other number has -1 its adjacency. So I'll say, okay, 2 is a number that's the lowest. So 2 plus 5 is X, and 10 is the largest number in such numbers. So 10 minus 5 is actually Y. This is actually equal to 7 and this is actually equal to 5. So this can be chosen as X and this can be chosen as Y. Now let's see. Now over here we only have this occurring case number 1, that when we found this segment, it had only one -1 in between. So I can just keep this as X. This is X, so X becomes 7. And is 7 satisfying the condition? I wanted less than equal to 5 differences. So okay, this difference is absolute difference is 1. This is actually 5. This is actually 3, and this is actually 2. So great, you are less than equal to 5 differences. Good to go. And this is a possible true case. Note this down in an answer and bring it over here. So you get 0 to 4 as a range now, and then you try to check again. Let's go. So you have 0 to 4 range, and you say, okay, let's find the mid. Answer, like this is currently your answer. You can say this is answer 0 to 4. Find the mid. This is 0 plus 4 by 2. This is 2. Now check with 2. Minimum value is 2. So 2 plus 2 is X, which is actually 4. And 10 minus 2 is actually Y, which is actually 8. So now if you keep a 4 over here, like if you try to keep a 4 over here, it's going to satisfy the condition that you have a less than equal to 2 difference with this case. But it's not going to satisfy the same thing with here. So you cannot keep a 4. Fine, X is not working. Let's try to keep Y. Let's keep Y. Y was kept. This is 8. Still not good to go, because this doesn't create a difference over here. It creates 6. Although it creates a 2 over here, but it doesn't create that place over here. So doesn't work, not good to go for me. So overall, this case turns out to be false. And I say, okay, move your, like it's not a noted answer. Potential answer is still 5. Move this to be 3. So I check a range from 3 to 4. Now I do a 3 plus 4 by 2. This turns out to be still 3. For 3, even if I find the answer turns out to be false. So like you can imagine this very simply. You say 2 plus 3, that's equal to 5. This is actually X. and this is 10 minus 3 equals to 7. So this is actually y. So if you place a 5 over here, then you will actually get difference as 3, but here the difference will be, absolute difference will be 5, which is not less than equal to 3, so not good to go. Same thing happens with 7. So this is not working, this is a false. Again move, like this is a false. So again move your range, this becomes 3 plus 1, so you get to 4. So the range now is basically 4 to 4. So effectively 4 plus 4 by 2, 4 plus 4 by 2, that is mid gives you 4 only. Check for 4, x becomes lowest next to 2 plus 4 is 6, y becomes lowest 10 minus 4, that is 6. Now if you place 6 over here, this actually works. 6 with this also gives you absolute difference 4, that is less than equal to 4, and over here also 4, this works. So 4 is a positive answer, it's a true answer basically, so it becomes a new active potential, and you can say answer has reduced down to 4, so this is our answer. And then finally we can exit the binary search because we have received the condition to be low less than equal to high, it's exhausted. You come out and you say 4 is your answer. Okay, now you can again take a case with more than one negative ones in between, and you will find that, okay, this simulation works in that case also. It's basically understanding that effectively every positive value that was there was introducing a boundaries, that was a plus max diff and a minus max diff. And when that boundary was clear, we wanted to stab, like basically we wanted to greedily stab two values x and y in all those intervals. And out of all such intervals, we wanted to stab x at greedily at the location which was lowest plus md, y at the largest minus md. That would have effectively made much more sense greedily, but then we always want to cross verify. That is why we ran checks in such a manner that after we placed x first, y first, because we generalize a is less than equal to b, so x is closer to a. When we placed x first and then y so on, we could have ran one more brute check on it and made sure did our x and y actually work. If it did work, then all intervals would have satisfied that condition. Good to go. That max diff is great. Make that as a true answer, make that as a potential answer, and decrement high as mid minus 1, else the other thing in binary search. Okay, so this is the whole idea. Let us try to see the code part now. It's going to be a bit lengthy. Let's see this quickly. So I have done something extra over here. Okay, this is what we are trying to do to just counter the base cases. We'll say that I have a missing count variable with me. That is basically how many numbers are missing, how many numbers are -1. And what I'm doing over here is I'm first counting what are the values of how many values are -1 in the array. Now why am I doing this is because I have some small cases I can just cover without even going to my binary search, that are, if let's say I find missing count as 0, that means no negative one number is there, so no number needs replacement. If no number needs replacement, you cannot do anything. You simply will have to calculate the maximum difference, absolute maximum difference, and just return that part, because that's all that can be your answer. You have no power in your hand to manipulate anything. That is why I simply calculate the max diff and I return it. Else, if I find that missing count is actually equal to the num size, that is all values are -1. If all values are -1, I can return a 0. Why? Because then I can set every number to be the same value. Let's say if I have -1, -1, so on, maybe I can turn all the values to x, 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 x. So absolute differences will turn to be 0 because every adjacent number is basically same. That is why I can return 0. Now, if all these base cases don't work is when I want a binary search. I'll start off with the low as 0. That is the lowest we could have created. And high as 1e. So I have taken as 1e 5 over here, 1e 9 plus 5. Then I have an answer variable. Okay. Now I do while of low less than equal to high, calculate the mid. If I find that this is a valid difference, then I know I want to try a smaller max diff. So I'll note this as an answer and I'll make high as mid minus 1, else I make mid plus 1 and I return this answer. Now, how do I calculate the checker function? First, I calculate the min and the max element of all such elements which had adjacently -1, because only those elements are going to affect. If the element does not have any -1 to its left or right, it doesn't introduce a boundary. It doesn't introduce that a plus max diff and a minus max diff in our case. So to calculate that, I have used a simple if check over here. I traverse the array and then I say, is this element not -1? Of course, it should not be -1. It should be some element besides -1. And does it have a -1 to its left, or does it have a -1 to its right? If any one of this condition is true, then I know I want to calculate I want to minimize my min element with this number, and I want to also maximize this simultaneously because I want to find the min and max of such possible cases. Once I have this on hand, I have the min value and max value. This is basically like x and this is basically y. So min value becomes minimum element plus max diff. That is what we calculated, a0 plus max diff. and this is a of n minus 1, the largest number that was there, minus maxdiff. Then you will try to, for every negative 1, fill it with either min value or max value. How do we do that? First we say, is this number negative 1? Yes, it is. So I will try to replace it. How do I want to replace it? I first want to replace it with min value. So to replace it with min value, it should satisfy the condition. It should satisfy the condition that if I place it with min value, then the left neighbor should have a absolute difference less than max diff, and the right neighbor, if it's there, should also have a absolute difference less than equal to max diff. If these conditions fulfill, then I will replace this with min value, else I'll replace this with max value. So preferred x first, then y. And then once I have replaced everything I wanted to do, I will have a brute check for myself so that I know I have handled the cases perfectly and everything is sorted. I'll say, okay, great. Find by brute manner, is every absolute difference giving me less than equal to max diff value or not? If anywhere this breaks, I will return a false, else I will return a true. Okay, now what is the time complexity? This is basically pretty much like you have, like you are running a loop over here. So this is like n order over here. And then this is directly giving us the return value. But over here, this is the main thing. You have a log space on a subspace of 10e9 order. So you can write this as log 2 of 10e9, right? 10e9 over here. And then you have this is valid function that is running in n order only. So you have n order over here, and then you have an n order over here also. So this is pretty much going to run in, like if I write the time complexity, O of n into log base 2 of 10 power 9. That's the subspace. So now this of course works for the given time limit. 10 power 5 into log base 2 of 10 power 9 is going to work. It's going to be within the boundaries, and this is effectively going to give me the right answer. What about the space? I'm using any extra space? Yes, I think I am. I have some space that of course comes from the nums array, and then I have some extra I think I have no extra space that is getting used besides the nums array. So I don't need anything extra. I can simply say that the space is dependent on O of n only. Both are definitely within my boundaries, so this gives me a correct solution. Okay, so it's relatively a very hard problem. It might not be very easy to visualize. It's going inside my head also, so I'm not very sure how this came off when we try to visualize this part. But then it would require, this problem would definitely require to pause the video and first try to give it one go yourself. Draw some cases, draw some visualized structure of number lines, and that is where you will be able to imagine which segments or which boundaries made sense, why did they make sense, and why did I take x and y to be that specific value. Once you understand that, binary search club with that part becomes very easy, and then all we want is simple checks. Okay, so this is all we had in this PCD. As explained, this last problem was very good binary search along with greedy solutions that was mixed in this. So that is something we cover in level 3 of TLE. So do check that out. You will find the links in the description of this video. So I hope you like the contest and the post-contest discussion for this. Thank you for watching.